Hello, welcome to our lecture 5. This is what I call Curiosities and Myths about the Brain. And what we're going to be talking about are some of the mysteries of brain action and how it's involved in behavior, and talk a little bit about um, the functioning of the cerebellum to give you a little bit of an introduction to this particular area. So again, we're going to be talking about some myths in terms of the brain and what I call curiosities about the brain. There's, I like to begin this by talking a little bit about some of my own experiences when I'm in a group of people who maybe I've met for the first time, and one thing kind of leads to another in terms of, talking about backgrounds. And um, when people find out that I'm a behavioral neuroscientist, I get interesting questions from them about the research that I do, and my thoughts about the brain. And just to give you a little bit of a background and experience in terms of some of the questions that I've fielded through the years. One of the ones that invariably I get is this question, is it true that we only use about 10% of our brain? And to be honest with you, I think that that's probably the number one question that I get from people, from the average lay person, and this is absolutely not true. And again, I don't know how this emerged, that people believe that we use such a very small part of our brain, but this is absolutely not true. This is absolute mythology. Another question that I very frequently get is this whole myth that's been perpetuated for many years about what we would call the Mozart effect. That is, if you play classical music to your newborn child, will that cause their brain to grow and make them smarter? There's absolutely no evidence whatsoever that I know of that would suggest that this is the case. Playing music might have a calming effect, perhaps, upon your child at times. There's some work that indicates that maybe this chemical in the brain that's called endorphins might be released as a consequence of soothing music, but there's no evidence that I'm aware of that indicates that this so-called Mozart effect, that is, of playing music to your newborn, is somehow going to make them smarter. It's going to make them more intelligent. So again, that's another myth. Um, is there a biological reason why the events in my dreams are so bizarre? We haven't really been able to pinpoint that. There's a lot of interesting work that we'll be discussing concerning sleep research, in which scientists have tried to correlate different biological changes with dreams, but there's no credible research that I'm aware of that indicates that there are very specific kinds of biological changes that occur in your brain with bizarre dreams. Another a popular question that I get from lay people is, are the brains of gay people physically different from the brains of straight people? And this is an area that we're certainly going to get into when we get to the whole area of sexual motivation and understanding the role, for example, that hormones play in terms of sexual orientation, and the genes play in sexual orientation. And there is some evidence to suggest that sexual orientation is related to genes, and it is related to how the brain seems to be different in those individuals that have different sexual orientations. That evidence, however, is evidence that is not in the realm of, I would say, overwhelming. We have a long ways to go yet in this area. Another question, interesting question, is why can't I tickle myself? And indeed, this is something that has been noted in many different cultures, been noted throughout the world, that you really cannot tickle yourself. You really do not respond to you yourself tickling your body in the same way in which if someone else was to tickle you, that you would experience a behavioral change. That question is an interesting one, and it's one that I want to pursue a little bit more as we go along. And I'll be talking about that in terms of the biology of it as we go along. But before we do, I want to tell you about an interesting book that I oftentimes recommend to new students of behavioral neuroscience. And it was a book that was written a few years back by David Linden. And the book is simply called The Accidental Mind. And the book is a very interesting one. The subtitle is, how brain evolution has given us love, memory, dreams, and God. And I encourage you to if you can, pick it up and read it. I'm going to be noting some interesting things about it as we go along, because I think it really does help us to conceptualize how we need to view the brain. So again, a recommendation, and one that you might want to take a look at. So David Linden, in his book, makes a number of very important observations. And one of his first observations is this: evolution is a tinkerer, it's not an engineer. And what he means by that is the brain really was not a product of this grand design of an engineer. That really it has evolved as a series of very interesting changes that has occurred as a consequence of our evolutionary history. So this whole idea of there being a grand design is not something that, at least from David Linden's perspective, is one that is viable. So when we take a look at the brain, you can see that series of ice cream scoops that you see here. And I think that this is the best way really to conceptualize the brain. We have these lower scoops here, we have these scoops that are in between, and we have these more recent scoops that you see here. So when you take a look at the functioning of the brain, breathing occurs here, biological rhythms, body temperature. This is all located in the very bottom, the oldest part of the brain. And things like homeostasis, for example, and biological rhythms, that's in these more intermediate layers that you see here. And what we know from our scientists that have worked in the area of evolution, evolutionary biology, evolutionary psychology, is that really the brain was built like an ice cream cone. We are the more recent scoops. That is to say, human beings, Homo sapiens, are these more recent scoops these are functions of higher cognitive processing, decision making. These things were added relatively recently. And again, they're placed on top of one another, these older scoops involved in basic biological processing. But these more recent scoops were ones that are really allowed us to advance in terms of language, allowed us to advance in terms of higher cognitive processing. So one of the things that I want you to do in this course in behavioral neuroscience is I want you to appreciate the fact that this is what many leading behavioral neuroscientists now believe, and that this is how they go about conceptualizing the brain. So the brain is inelegant. And again, this is David Linden who has advanced this concept. But what we have in the media is this thing that we call brain worship, which I think is very unfortunate. You hear things like on a show, let's say, about the brain, something that you might watch on PBS, for example, that the brain is an amazingly efficient 3 pounds of tissue. It's more powerful than any supercomputer. That is the seat of the mind, the pinnacle of biological design. And I think that when you get that kind of brain worship that's constantly being advanced, the conclusion is that our brain is very, very efficient, that it's very elegant, that it's very well engineered, that it's optimally designed. And really, that is not a truthful statement. And I think David Linden in his book has done a good job of debunking this mythology that has been perpetuated, I think, by the media and by those that are involved sometimes in the field of science writing. So David Linden's his take on the brain, I think it's very important to reflect upon that. He says the brain is inelegant. It's inefficient. It's an agglomeration of stuff, but it really works, quite well. But let's get away from this idea of this, supercomputer or super elegant engineered brain. That's simply not true. It is not a general purpose computer. It was not really particularly well designed if you go back in terms of our evolutionary history. It reflects millions of years of our evolutionary history. And again, we're going to be talking about evolution soon because it's such an important part of the field of behavioral neuroscience. Linden says in his book, there are many examples of how we have adopted solutions for various problems. And again, these are things that have persisted over time, and our brain is constantly recycling parts of our brain to use for other things. And again, we have to think of this constant kind of change that occurs over the course of our evolutionary history, where, at one point it was very good for solutions for certain problems, but those solutions are ones that are no longer needed, and hence, that part of the brain may be adopting another purpose as we go along in terms of our evolutionary history. So I think that that's something that needs certainly to be considered. So here's a good example of brain function. I want to talk about the cerebellum a little bit. Here's the cerebellum that you see right here in the back of the brain. Cerebellum is involved, of course, in coordinating our body movement. And it's constantly using feedback. It's using feedback from your body, from various parts of your body as you move through space. And it's enabling these fine motor skills and these corrections to take place so that you are well coordinated. So again, the cerebellum, very, very important part of our brain. Now, when we take a look at the cerebellum and what happens when it's damaged, and again, here's our cerebellum right here. Damage to the cerebellum is subtle. It's not going to paralyze you, for example, but typically what is going to happen is you might be a little bit clumsy in terms of performing tasks that at one time were very easy for you now become much more difficult. Reaching for a cup of coffee, for example, something that you could easily do at one time, but when you have some damage to your cerebellum, you can't do it as well. Walking with a normal gait. You could easily do that prior to the damage to the cerebellum, but after that, you can't do it as well. The phenomena that is called ataxia simply means a lack of coordinated body movement. So again, the damage to the cerebellum, relatively subtle when that damage does occur. But it is reflected in this phenomenon that we refer to as ataxia. So the cerebellum really is involved in our expectations. It is involved in terms of distinguishing those things that we expect to occur versus those things that we do not expect to occur in terms of our environment, in terms of being stimulated by our environment. So whenever you start a particular movement, you have direct sensations that come from that movement. And what happens is you don't pay very much attention to those things. And again, the really great example of this is in terms of when you are walking and your clothes are rubbing up against your body. You ignore those things, and the cerebellum is involved in that. The cerebellum is involved in ignoring those kinds of sensations that you feel on a relatively constant basis. But take the following example. If you were just, let's say you were standing somewhere and unknown to you, someone came up and grabbed, your leg, and you didn't see them at all. They came up from behind. You would pay a lot of attention to that, and no doubt you would probably turn around and you look at what was happening to you, the sensation that you were not expecting at all. It's very useful to ignore things that you're constantly being exposed to, that continuous kind of stimulation, versus things that are coming at you from the outside world that are unexpected. And indeed, the cerebellum is involved in that function. The example that I like to give is, when one of my boys was very young, he hid underneath the bed in our master bedroom. And my wife was up there one day doing some things in the bedroom, and he was hiding underneath the bed, and all of a sudden he grabbed the leg of my wife, and she let out this shriek and this yell. Again, it was because it was so unexpected. So again, your cerebellum is involved in making these distinctions between what is constant and expected versus those things that are not expected. So again, expectation and cerebellum function. Cerebellum is constantly receiving signals from many different brain regions, and they are, involved in creating these commands that trigger our body motion. The cerebellum is using these signals all the time to predict sensations that are predictable, ones that are likely to result from that motion. And it's inhibiting parts of the brain, regions of the brain. It's telling, hey, this is expected. And again, it's differentiating that from the total number of sensations that you are feeling. So again, cerebellum and expectation, very important function. So now let's get into this whole thing of, why you can't tickle yourself, which I think is a fascinating question, which has a definite, physiological kind of explanation for it. So again, this is something that we see in all cultures. It's very well known that you can't tickle yourself. And David Wolpert neuroscientist, has set out to examine this, to explore it. What you see on the right-hand portion of the slide here, this is a functional MRI of a subject. That is being tickled by someone. And again, this is the somatosensory area that we see right here, and you're getting very, very strong activation that is occurring. And if you were to take a look at the cerebellum, there would be very little activation that was taking place when you were being tickled by someone. When you tickle yourself, on the other hand, you get a little bit of activation in the cerebellum. You get a spot of activation that occurs and greatly reduced activity in the somatosensory cortex. So the cerebellum is serving this important role now of, differentiating between what's expected and what's not expected. So again, this is a, confirmation, really, these fMRI images that Wolpert has been able to produce in both the cerebellum as well as in the somatosensory cortex. So physiological explanations for tickling, again, these hand motions that are involved in self-tickling. The cerebellum is being stimulated, it's forming this prediction, and it is sending signals about this to, suppress the somatosensory cortex. Here's the somatosensory cortex of our brain right here. That reduced activation of the somatosensory cortex then is below the threshold that is needed in order to feel that sensation of tickling. Now, very interestingly, human beings who have sustained some damage to the cerebellum, they can't generate those predictions the way in which a normal cerebellum does, those expected sensations, and therefore they can't really tickle themselves. When there is damage, on the other hand, you can actually tickle yourself because, again, you don't have those generated kinds of predictions that are occurring, those expected sensations that are occurring. So, in fact, a human being who has sustained this damage to the cerebellum, they cannot generate those predictions of expected sensations, and as a result of that, they can actually tickle themselves. Very interesting. So this last slide, I want you to think, this is a good analogy to keep in mind when we're talking about the organization of the brain. It's what I call the Model T analogy. Let's say that you are asked to build a modern car, but the stipulation was that you had to use the chassis, okay, of this old car, of this Model T, in order to produce this new car that you see right here. You had to use the same chassis, okay. This is really, in my view, a perfect analogy to what I'm talking about in terms of the brain and the organization of the brain. So again, building that car with a Model T chassis, you can only add parts to the existing structure. That's identical to the brain in terms of the building of the brain, in terms of our evolutionary history. The old parts of the brain are unchanged. It's those most recent scoops that are really critical in terms of the human being. In our evolutionary history, in terms of the development of cognition, the development of human awareness, the development of this advanced decision-making and language, for example, the ability to anticipate the future. These are functions of what we would call the new brain, these more recent scoops. So again, that's the kind of picture that I want you to keep in your mind as we go along. So, in our next lecture, we're going to be talking really about evolution and our evolutionary history, and learn a little bit about that. as we begin to get into the whole area of genes and the contribution that genes play in behavior.